Hello everyone, hopefully you're having a really good day. As you can tell, I'm not in the classroom today, and so we're going to go back to our video notes, but you're going to do this in class. And so if you need at any point to have the teacher pause the video, just raise your hand and let them know, and they'll pause the video to let you get caught up. But hopefully these notes should come pretty easy and should be pretty easy for you guys to understand how to find geometric probability. And that's basically using probability just like we normally would, but it allows us to use geometric measurements of length and area to help find different probabilities when there are an infinite number of possible outcomes for our given events. All right, let's get started. First thing I want us to understand is what geometric probability actually is. Geometric probability is probability that involves a geometric measure such as length or area. And so the first one we want to talk about is the length probability ratio, and here's what we have. Okay, let's say we have a line segment 1 containing segment 2. So AD would be our line segment 1. And BC would be our line segment 2 in this case. And a point at random chosen from segment 1, then the probability that the point is on segment 2 is the length of segment 2 over the length of segment 1. Or in this case, if I placed a point randomly anywhere along AD, that would be my sample space, the probability that that point would be between B and C, or on segment BC, is the length of BC divided by the length of AD. And so we just take the two lengths and we divide them out, and that's how our probability is given. Remember, we could write this as a fraction, a decimal, or a percent. All right, so let's take a look at example 1. We're going to choose point Z at random on segment AD. That is our sample space. We want the probability that that point chosen at random is on segment AB. And so that probability is just the length of AB over the full length of our sample space AD. Well, the length of AB is 2 units. The length of AD is 2 plus 2 plus 7, or 11 units. And so 2 out of 11 is how we can express that probability. Okay, and we can apply this to a situation like this. Halley's Comet orbits the Earth every 76 years. What is the probability that Halley's Comet will complete an orbit within the next decade? Remember, a decade is 10 years. We can actually write this out as a timeline. Okay, we can start from 0 out to 76 as the cycle of the orbit for Halley's Comet when it orbits the Earth. Now, the probability that it will complete an orbit within the next decade, we don't know exactly where we would currently fall in that 76-year orbit, but we could pick any space of 10 years on this timeline and represent that as our decade in our next decade. So it really doesn't matter where we space out a 10-year segment. We know that it would have a length of our timeline of 10 out of a total of 76 years. So the probability for a passing of the Earth in the next decade would be 10 over 76. Now, we do want to reduce that if we can, and that would definitely be able to be reduced because we can divide both of them by 2. That would be 5 over 38. Sorry for that delay. All right, now we can also talk about probability when it comes to area measurements also. And so we have our area probability ratio. Let's say we have some region A that contains region B. So the area of region B has to be smaller than the area of region A by definition. And we're going to select point E at random anywhere in region A of our sample space. Then the probability that that point is in this other region B is the area of region B out of the area of region A. So specifically here, we have the area of a circle and area of a rectangle. And so the probability that our point E is in circle B is the area of the circle B. Remember, area of a circle is pi r squared, okay, out of the area of rectangle A, which would be length times width or base times height. Okay? So let's move on to example 3. The targets of a dartboard are formed by 3 concentric circles. Remember, concentric means they have the same center and they are getting bigger towards the outside. If the diameter of the center circle is 4, it's hard to see, but we can say the diameter is 4, and the other circles are spread 3 inches apart, what is the probability that a player will throw a dart into the center circle? Well, here's what I want you to look at. Okay, the radius of the smaller circle is 2, and then this segment of white space to get to the other circle is 3, and then this segment would also be 3. And so from this we can come up with our radius of the smaller circle or central circle, and we should be able to come up with the radius of the largest circle to get our total sample space. We're assuming that our dart would land on the target somewhere, not over here on the wall. So the radius of our central circle is 2 inches. The radius of the largest circle is 2 plus 3 plus 3. And the reason we need that is because we're using the area formula for a circle. Area of a circle is pi r squared. So the probability of a point being, or a dart being thrown in the center circle is pi times that smaller radius squared over pi times this larger radius squared. 2 plus 3 plus 3 is 8 inches. Now what you notice about this when we do our probability ratio, the pi values cancel out. And 2 squared becomes 4, 8 squared is 64, and if I divide both of those by 4, I get 1 out of 16. So the probability of landing in the center of the circle is 1 out of 16, because we found the areas of both. And we didn't actually have to calculate the areas in terms of pi. We could cancel the pi's since they're both circles. That will not always work out that way. It's only because everything is a circle in this example. All right, let's finish up with example 4. We can also use degrees of a circle, like in a pie chart or in a spinner. So here's our spinner that we have for these next 2 parts of this example. Okay, we want to first select the probability of the pointer landing on section 3. Well, that's 122 degrees out of the total 360 degrees of our spinner. So that probability is 122 out of 360, which is 61 over 180 as a reduced fraction, but we can go ahead and round that as a decimal as about 0.34, or approximately 34%. All right, part B, the pointer landing on section 1 is only a 26-degree arc, and that's out of our 360, which would reduce to this, 13 over 180, or approximately 0.072, which is about 7.2%. All right, and that actually wraps up the notes portion of this, but in order to help give you guys a little bit of extra guidance, I do want us to maybe do a couple of these, or I'm actually going to do a couple of these for you, and give you some explanation of the homework assignment. This is the homework assignment you should have been given at the beginning of class, but if you don't have a copy of this, please make sure you raise your hand and get one now. Otherwise, we will go ahead and take a look at a couple of these. I'm going to help you out. I'm not going to work everything out for you. That would not make this homework. It'd be notes again. But I am going to give you some pointers. These first 4 are just like example 1, but I throwing in some other verbiage, some other words to include in your probabilities. Like on number 2, when it says the probability that x is not on NO, we're going to exclude that segment from our sample space to get our event. That means you can have every other possibility except that. And so your favorable outcome, your event, would be the sum of these other segments. And also number 4, when it says LM or OP for our placement of x, that means you would add LM and OP lengths to get your desired outcome. All right, for the rest of these, you're going to be using your area probabilities. And on some things, I actually give you the measurements to be able to use. And so pay attention to the directions that it says find the probability that a point chosen at random lies in the shaded region. Well, here the shaded region is a circle. Okay, so to do this one, you would take the area of the circle over the area of this other shape. Well, this is a square. Okay, the side length of the square would be the diameter of your circle, so the side length is 4. And so you should be able to find the area of a circle and area of a square, divide those out, and go ahead and write these as decimals to the nearest hundredth. That's where we're going to round these, unless you don't have to round. Sometimes you won't have to. Okay, but on number 8, you'll notice the shaded region is now not the circle. So what you would do is take the area of the square minus the area of the circle to get these shaded portions, and divide that by the area of the square. Okay, same dimensions as number 6 though. Excuse that message. All right, but I want to show you about numbers 5 and 9. Notice I don't actually give you the measurements. That's okay. You can tell that the shaded regions are parts of congruent portions of the overall figure. So even though this is a hexagon, we don't have to use our apothem times perimeter divided by 2 area formula. All we have to notice is that these 2 shaded triangles are congruent to the non-shaded triangles, and so there are a total of 6 triangles in the hexagon. 2 of them are shaded. Our probability would just be 2 out of 6, or 1/3. Now, since I said to round to the nearest hundredth, this time I will let you write this as 0.33, or approximately 33%. And you're going to do number 9 very similarly to that. We have 3 shaded squares out of a total of 9, and you can work that out the same way we did number 5. Again, excuse the messages. All right, and that should get you through, or get you started on our geometric probability lesson. If you have any other questions, bring them in on Friday, and we will talk about those before we turn this in.